Hi there, welcome back. This, I think, is lecture 13, which you're probably watching on Tuesday. Remember, we've got an exam coming up on Friday. We're going to review on Thursday. So this is the last of the new material that will be covered on the exam. If we have an invertible matrix, so let's say, suppose A is invertible, then if we consider the system, so we can solve the system AX equals B in two different ways, right? Right now we have two different ways. What we could do is set up an augmented matrix like this, do row operations, get this in reduced row echelon form, and then we'll be looking at the unique solution. So there's one way to do it. Another way to do it is to say X equals A inverse B. So if you want, you can compute the inverse matrix, multiply A inverse times B. The unique solution X is equal to A inverse times B. So at this point we have two different ways. We're about to learn one more way to compute the solution to the system AX equals B in the case that A is invertible. So let me say this a little more precisely. The unique solution to the system AX equals B is given by, let's say given by, X equals A inverse times B. And remember, we learned last time that we can compute the inverse of A using this adjoint method, right? So this looks like this is 1 over the determinant of A times the adjoint of A. So here's a matrix, and then we multiply that by our column vector B. Now, let's write out, so let's say letting X is a column vector, so I want to actually write out the entries here, x1, x2, dot, 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 down to xn. And also I want to write out B, so B is also a column vector, b1, dot, 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 down to bn. What we have, right, so we get X is equal to, so let's actually write this out, 1 over the determinant of A times, so let's see now, who is the adjoint? Well, make sure I got room here. The adjoint is going to be the matrix of cofactors, or actually it's the transpose of the matrix of cofactors. So this would go like this, C11, C21, C31, dot, 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 CN1, dot, 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 dot. This would be C1N, C2N, dot, 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 CNN. And notice, now I took the transpose of that matrix of cofactors, so you can see what I have here is the first subscript is actually changing, right? Because we've swapped the rules of row and column. Okay, so here is what the what X is going to look like. And let me actually write this. Sorry, times B1 up through Bn. So this right here, we've got 1 over determinant of A. Here's the adjoint of A, and then here we're multiplying by B. And I want to keep going with this. So this is equal to 1 over the determinant of A. And now I actually want to do this matrix multiplication right here. So we're going to do row dotted with this column right here to see who the entries are. So what we will have is B1, C 1, 1 plus B2C 2, 1 plus dot, dot, dot plus BN CN1. And you keep doing this, second row dotted with that. And then when we get to the last one, it's going to be B1 times C1N plus B2 C2N dot, dot, dot. And eventually we get to BN CNN. So what that tells us, remember, we have xi now equal to this column vector, or x is equal to this column vector right here. So xi is equal to 1 over the determinant of A times B1 C1I plus B2 C2I plus dot, dot, dot plus BN CNI. So now what I want to do, I want to write xi in sigma notation. What we get is x sub I is equal to 1 over the determinant of A times the sum. Let's use, I used I already, so let's do, what do I use, J? I'll use K. K equals 1 to N. B sub K times C K I. Okay, so that tells us now who the entries to our solution X are, right? X is a column vector. This tells us who the entries are. And that should say B sub K right there. Okay, now let's let A sub J be the n by n matrix obtained by replacing the jth column of A with the column vector B. So it's going to look like this. So A sub J is going to be, well, it'll go A11, A12, dot, 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 and then we will have A, so I want the J, I want to replace, so this is A sub 1, J minus 1, B1, A sub 1, J plus 1, dot, 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 A sub n. And you keep doing this, so what we're going to see is we're going to see B filling out the jth column. So this is the J minus 1th column right here. This is the J plus 1th column. And so if you keep going, so we'll have an A21, A22, dot, 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 A2 sub, A2 times, or A2, J minus 1, B2, A2, J plus 1, dot, 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 that should be A1N, that should be A2N. So sorry about the double subscripting with these J minus 1s and J plus 1s, but just to keep our head straight, this is the entries in the J minus 1th column, the J plus 1th column, and then the B's are going in the Jth column. So this last one will be an AN1, AN2, dot, 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 ANJ minus 1, BN, ANJ plus 1, dot, 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 ANN. Okay, so here's my matrix A sub J. And what I'd like to do is I want to take the determinant of this matrix right here, and I want to do it by expanding about the jth column, so expanding about these b's right here. So, the determinant of a sub j is equal to well, it's going to be b1 times minus 1 raised to the 1 plus j times the determinant of, okay, so what are we going to do? We're going to delete the jth column and the first row. So who is that? That is a sub 1j plus blah, blah, blah. Eventually we'll get to b sub n minus 1 to the n plus j determinant of a sub nj. Who's that? That's b1 times c1j plus dot 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 plus bn c sub nj. Each, like that right there, that's the njth cofactor. That's the 1jth cofactor right there. So what do we have then? Notice that the determinant of this matrix that we got by replacing the jth column with the b's exactly matches this summation right here. If you put a j right there, you get a j right there. And so what does that tell us then? Let's write this up now as a theorem. Okay. And this theorem actually has a name. It's called Cramer's rule. So it goes like this. If capital A is invertible, and A sub j is the matrix obtained by replacing the jth column of capital A by the column vector B, then the unique solution X equal to A inverse times B is given by X equals x1 dot 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 down to xn, where X sub j is equal to 1 over the determinant of A times the determinant of A sub j. Okay, so that formula right there gives us a third way to solve linear systems in the case that we're dealing with an invertible coefficient matrix. Right. And so this tells us exactly how to find each of the entries to this unique solution. It's right there. Let's see Cramer's rule in action now. we're going to do a 3 by 3 matrix. So let's have A equal to the matrix 1, 2, 0, 0, 1, 2, and 3, minus 1, minus 1. And B is going to be the vector 1, 0, minus 1. And what I want to do, I want to solve the system AX equals B by Cramer's rule. So step 1, take the determinant of A. So the determinant of A, that's going to be 1 times minus 1 plus 2, so that's a positive 1, minus 2 times negative 6 plus 0, so that's going to be a positive 13. Okay, now I look at the matrix A1 that I get by replacing the first column of A with the matrix B. All right, so there's the matrix A1. I compute its determinant. The determinant of A1, that's going to be a 1. That's negative 1, negative 1 minus a negative 2. So that's negative 1 times 1 minus 2 times negative 2. No, something's wrong here. Minus 2 times, times positive 2. So that gives me a negative 3. The matrix A2. So what do? I replace the second column of A with the vector B. So this will be a 1, 0, 3 for the first column, 1, 0, minus 1 for the second column, and 0, 0, 2, minus 1. In this case, notice I've got a couple of zeros here, so it's probably best to compute by expanding about the second row. So let's see, this is the 2/3 entry, so this will be negative 2 times negative 1 minus 3, so negative 2 times negative 1 minus 3, that looks like positive 8. Did I get that one right? I'm just going to check my answer here. Yep, positive 8. And then we've got one more. So A3, that's the matrix that we get by deleting the third row and replacing it with B. So that will be a 1, 0, 3. 2, 1, minus 1. 1, 0, minus 1. Once again, I'm noticing here I've got 2 zeros in this row, so I'm going to once again expand about the second row. The determinant of A3 is going to be 1 times the determinant of the matrix I get by deleting the second row and the second column, so that will be a negative 1 minus 3. So that'll be a 1 times negative 4 minus 4. All right. So now X is equal to, so what do? The first entry is negative 3 divided by 13. Second entry, 8 divided by 13. And the third entry, negative 4 divided by 13. That is exactly the same answer that you would get if you computed A inverse and multiplied it by B, or if you did row operations and reduced the augmented matrix that looks like A, B, get the same answer. So this is one more way to compute the solution. I think of Cramer's rule more as a theoretic process or a theoretical result. I don't use it a whole lot in practice, but it does work, and in this case it actually was kind of nice. All right, see you next time.